This lesson introduces you to cubic functions. So far, we've been looking mostly at quadratic functions. So we'll do a brief review of quadratics and then compare them to cubics. Remember, quadratic is a second degree. So in general form, we can write it as you see on the screen in green. And because it's quadratic, the highest exponent on the variable x is 2. If we extend our study to include cubics, well, the general form for a cubic, now we can have up to an exponent of 3. So we could have an x cubed, an x squared, an x term, and then, of course, a constant. So now we'll be looking at functions that might have up to 4 terms in them: a cubic, a quadratic, a linear, and a constant. As you recall, there are other ways to write quadratics. A very useful way of writing a quadratic function is in factored form, and it turns out that we can basically do the same thing with cubics. It's just that since it's cubic, there's now 3 roots, r1, r2, and r3. Remember, roots are values that when you plug them in for x, the function equals 0. We had one more version of our quadratic, and that was vertex form, and that revealed the vertex of the parabola. We don't have something like that for cubics because, as you'll see on the next screen, when you graph a cubic function, you don't get a parabola. You get a different sort of shape, and so cubic functions don't have a vertex, so we don't have a vertex form. Okay, so let's actually look at a specific example. When a function's written in factored form, it's pretty easy to determine its x-intercepts. So remember, an x-intercept or a root is a place where the function evaluates to 0. So notice that if you plugged in a 5 for x, 5 minus 5 is 0, and it wouldn't matter what these other things were. 0 times anything is 0. So that tells us that 1, 2, 3, 4, 5, there should be an x-intercept, because when x is 5, y is 0. Similarly, if you look at the second factor, x minus 2, we know that if we plug in a 2 for x, we'll get 0 for the value of the function as well. And then our third x-intercept is going to be negative 4. 1, 2, 3, 4. So we know those are the x-intercepts of our graph, and in general, if it's a third degree function, there could be up to 3 x-intercepts. Now, in order to get a little bit more detail for this graph, it's a good idea to find a y-intercept. So I'm going to plug in a 0 for x. So let's erase this 5, and then let's think about plugging in a 0 for x. If this is 0, and this is 0, and this is 0. Then to find the y value, we're going to have to do 0.2 times, well, 0 minus 5 is negative 5. 0 minus 2 is negative 2. And 0 plus 4 is 4. So if I multiply negative 5 times 2, that's positive 10. We have a 4, and we have a 0.2. So maybe parentheses would make this a little clearer. The 10 times 4 is 40. And you can check this if you want on your calculators, but 0.2 times 40 is going to be 8. So that means that the y-intercept is 8. In other words, when x is 0, the function evaluated to 8. Okay, now that you have these 4 points, it would be reasonable to try to sketch the graph. So there you have not a perfectly drawn rendition. You can graph it on your calculator if you want to see a more accurate graph, but that was the basic idea, and that is the basic shape of most cubic functions. Most cubic functions are going to look something like this, or they might look like that. Okay, so that's just the basic shape. Doesn't have a name, it's just the shape of a cubic function. Okay, so Now we're going to sort of do the reverse. This time I've given you the x-intercepts, or rather I've given you the graph, and from the graph you can find the x-intercepts and write it in factored form. So you know in general that any cubic can be written in factored form. The leading coefficient is a, and then there'll be 3 factors, one for each x-intercept. So in this case, y equals a times, well, this is 1, 2, 3, 4, 5, 6, 7. So if it's negative 7, then the factor is x plus 7. This one's negative 2, so the factor is x plus 2. And this last one, 1, 2, 3, that would be x minus 3. Okay, we still need to figure out what a is. So you can use the y-intercept or any point, other point on the graph to find a. So if you look at the y-intercept here, it's 0, 7. That means we should get a 7 if we plug in a 0 for x. So 0 plus 7 is 7. 0 plus 2 is 2. 0 minus 3 is negative 3. So we get 7 equals, let's see, 7 times 2 is 14. And 14 times negative 3 is negative 42. So 7 equals negative 42a, dividing both sides by negative 42. And I discover that a is 7 over negative 42, which I could reduce to negative 1/6. So that allows me to write this function. I can now replace this a with negative 1/6. Again, if you graph that on your calculator, you might get a more accurate graph. I don't know, it might dip lower here. But that's the basic idea of how you can use a graph to then write the function. Okay, so for your homework, number 1, I want you to find the 3 x-intercepts and the y-intercept for this function. Remember, each factor, x plus 7, x minus 9, and x plus 14, should give you an x-intercept, and to find the y-intercept, you plug in a 0 for x. Okay, on number 2, I give you 3 x-intercepts. That should allow you to write the cubic function in factored form. And by telling you the y-intercept, that should allow you to solve for a, the leading coefficient. That's very much like what I did on the previous screen, except that there was a picture rather than words. Okay, number 3, this is going to ask you to sort of think beyond this tutorial. Graph the function on your calculator. Look at it to find the 3 x-intercepts, and then use those x-intercepts to write the function in factored form. As far as the leading coefficient a, since right here it's just 1x cubed, you don't have to worry about the leading coefficient, it's going to be 1. Okay, please have that ready for class next time.